So during this session on static inventory problem under risk, I am going to discuss the type 3 problem. Already we have discussed say the type 1 problem and the type 3 problem, type 2 problem. So now I will be referring to type 3 problem, and then an important issue we are also going to discuss during this session, that is the opportunity cost matrix. And this opportunity cost matrix concept I intend to discuss with referring to say the type 1 problem. Okay, and opportunity cost is also known as the regret matrix, and what we will get a different so the idea about the stock out or overstock situation, and for both the cases you need to calculate or need to get an idea about the opportunity, the cost due to loss of opportunity. So this is an important concept to be used or to be understood while we go for say developing an inventory control systems. There will be few numerical problems also we are going to discuss. Now let us first talk about the type 3 problem. As I have already mentioned that the type 3 problem, in type 3 problem the demand is considered variable, and so also the lead time. So it's a variable demand and variable lead time case. So this is a complex problem, right? And the problem can be modeled assuming either demand and lead time independent or dependent with each other. Okay, so in many a time the mathematical even if you go for mathematical the modeling for such a problem, but you may not get a solution in closed form. So many a time you opt for the next best alternative, that is the simulation approach. Okay, so in course of time we will be discussing the simulation approach in inventory control modeling. So that point in time we will be discussing these aspects also. So this problem can be modeled with lead time set at its maximum level. So that is just one type of compromise we make many a time. That means you say the variable lead time, so why don't you collect the data on the lead time and you model the problem as per the maximum on the lead time. So that is just one approximate solution you might get. Okay. Now so let me say first explain this problem, and there will be certain say the parameters, certain variables we will be referring to while we model this particular problem. We are referring to as the type 3 problem, variable demand, variable lead time. If D bar is the average demand per day, okay, L bar this average lead time length in days. Okay, so that means the lead time period actually. The number of say the measuring unit is a day. Sigma D is the standard deviation of demand, and sigma L is the standard deviation of lead time. Okay, so and sigma is the standard deviation of demand during lead time. Okay, so when the demand and the lead time distributions are independent. Okay, this is just this is the first assumption we are making. So this is if this is the case, average demand during lead time. So the notation is M bar. Okay, so the M bar equals to D bar into L bar. Okay, so this is the average demand and this is the average lead time. So if you multiply them, that means you multiply one with the another, you get the average demand during lead time. But then how to calculate the variance of demand during lead time? So the notation is sigma square, and this is the formula we use, like L bar square sigma d square plus d bar square into sigma L square. Is it okay? So that means this is the average the lead time, square of average lead time into the demand, the variance of the demand, and this is the square of average demand, and this is the variance of the lead time. Is it okay? So this formula we use when the demand and the lead time distributions are independent. Okay, so we will be considering actually that whether your inventory control system is suitable, or it is perfect one, or it's working perfectly during the lead time. Is it okay? So that's why so the average demand during lead time is an important factor to be considered, and the variance of demand during lead time. Is it okay? So as I've already mentioned that whenever you try to propose an appropriate inventory control system, make sure that during the lead time there should not be any stock out situation. So the stock out situation, and as you may be knowing that there is a possibility of the stock out occurs because of the two reasons. That means the fluctuations of demand and during lead time, as well as the fluctuations of lead time itself. Is it okay? So this is the case. That means if there is a variable demand as well as the variable lead time, so you need to say while you design an inventory control system, you have to keep some extra stock, and this extra stock of item is referred to as the safety stock or the buffer stock. So the whole exercise actually boils down to the determination of the safety stock. Is it okay? Determination of the safety stock. Later on we'll take up these issues in much the detail. Now the second case could be when the demand and the lead time distributions are assumed to be the dependent or not independent with one another, with each other. Average demand during lead time is m bar equals to d bar and L bar, like in the previous case, whereas the variance of demand during lead time, it will have an added component, that is sigma d into sigma L. So the sigma square, that means the variance of demand in lead time, these notations we have used, that is L bar square into sigma d square, that means is the variance of demand, plus the square of average demand into the lead time variance. Is it okay? Plus the standard deviation of demand into standard deviation of the lead time. So okay, so you refer to the notations we have used, and I think that that there will be no problem in understanding the expressions which we need to use. Now so this is for the problem type 3, and frequently we come across in the real world, we come across problem type 3. Okay, so later on we'll be referring to this case and we'll discuss it in much detail. Now at this point in time, I like to bring in the concept of, I like to discuss the concept of opportunity cost. Okay, so as you are already aware that the given a problem, okay, with all the the required data given, you need to construct the payoff matrix. So the concept of payoff matrix is made very clear. It is well understood. Now from the payoff matrix, in many a time you make the opportunity cost matrix, or the original payoff matrix can be converted into opportunity cost matrix. Now let us first take the type 1 problem. That means type 1 problem means that variable demand and constant lead time. Okay, and we will discuss the opportunity cost matrix concept for the type 1 problem. Now the payoff matrix of the problem can be converted into the opportunity cost matrix. So given a type 1 problem, what you need to do, first you construct the payoff matrix. So the payoff matrix can be either in the form of say the profit, or in terms of say the cost. So whatever it is, the payoff matrix of the problem can be converted into the opportunity cost matrix. How we will convert it, I will tell you in detail. The payoff can be either of profit, okay, actually contribution to profit, this point already I have mentioned, or of the cost term, depending on the type of problem. Is it okay? So if it is an outside the supply case, the sales is involved, then obviously the payoff you compute, or the payoff or the outcome in terms of the profit. But if it is an inside supply case, only the cost related the terms are involved. So obviously the payoff or the outcome you define in terms of the cost. The best decision is if order matches exactly with the demand and opportunity cost is 0. So what is this opportunity? That means whenever, say suppose the order quantity matches exactly with the demand level. So obviously it is the best possible the situation, and what you expect that so against that particular combination you get a payoff or the cost. Is it okay? So it is just the best possible matching, and obviously there is no opportunity the lost. So the opportunity cost is assumed to be 0. Okay, for all other combinations, when suppose the demand is more than say the order quantity, or the demand is less than the order quantity, okay, overstock situation, so always there will be some the loss due to cost due to loss of opportunities. So opportunity cost will be there in any other combination. So for all other cases, when either order is more or less than the demand, this point already I have mentioned, there is an associated opportunity cost. Okay, so when we take up the numerical problem, so this will be made, this concept will be made more clear. Okay, now the relationship between opportunity cost and payoff is given by, that means given a problem, like so suppose the problem say so the benefit analysis you have to do, and it is a payoff matrix, and the payoff matrix is in terms of profit. Okay, so that is the problem type you have taken up. So in that case, the expected opportunity cost for a given strategy, that means for a given order quantity, will be K, capital K is a constant, minus EF. EF, what is that? That means for the given strategy, say strategy is I, order quantity is I, what is the expected payoff? Is it okay? So this is the relationship. You can very easily you can prove that EOC is equals to K minus EF if the original payoff matrix is in terms of profit, whereas if the original payoff matrix is in terms of cost. Is it okay? Then the relationship is EOC, expected opportunity cost for a given strategy, is equals to expected payoff in the cost terms, obviously expected payoff in cost terms for that particular strategy minus the constant, that is capital K. So this we have elaborated, we have explained. That means EOC is expected opportunity cost for the given strategy, that is the order quantity. EF is the expected payoff for the given strategy. Given strategy means essentially the ordering quantity or ordering strategies. And capital K is the expected value of payoffs if the best course of action, order matching with the demand, is always taken. That means essentially it is what we will find that the payoff, the values in the diagonal of the matrix. Okay, so the best possible the situation. So obviously this is the maximum or the minimum value you get, and that is essentially constant. Okay, so the K is a constant. So when you take up the example, it will be made more clear. So we can calculate the EOC, expected opportunity cost, for each order quantity. The cost of risk for a particular strategy given by the difference between EOC for the strategy and K. So there is a concept called cost of risk, right? That means you place an order quantity, and this may not be the best possible decision. Is it okay? So always there is a risk, and there is a risk, and the corresponding cost of risk you need to calculate. So essentially the difference between, say, the K and the expected expected payoff is referred to as actually the cost of risk. Is it okay? So the cost of risk for a particular strategy is given by the difference between EOC for the strategy and the K. Is it clear? So this way we interpret the cost of risk. Now here is an illustrative example. Now X is the amount order, J is the demand level, okay, for the given the inventory item, right? So we are considering one item only. Is it okay? So all these analysis, all these concepts we are trying to explain with respect to one or the single inventory item. The demand distribution is given by, say, as you find in this table. That means the possible the demand levels are 1, 2, 3, 4, 5, 6 possible demand levels. So the corresponding probability, assuming it to be objective probability, that means the frequency based on the frequency counts. So you have determined these values, and so against the demand level 1, the corresponding probability is 0.05, against demand level 2, 0.15, and so on. Is it okay for other levels? So against the demand level of 4, the probability is 0.40. That means 40% of the cases the demand level will be 4 units. Okay, so the total is just 1, the probability. Okay. Now obviously with the given the problem, you will come to know what certain data will be given related to the price and the cost. So the unit price of the item is considered to be 6. Okay, purchase cost is 2. Okay, unit salvage value 0.50, unit delivery cost 0.50 again. Is it okay? So that means whenever the demand occurs and you make a supply, and for each supplied item there is a delivery cost. Is it okay? For each supplied item, and that cost is $0.5. Similarly, if there is an overstock situation, that means you are unable to sell it, so you can sell it with a reduced price, and you have some certain salvage value. So salvage value per unit is assumed to be $0.5. The cost of say the purchase cost per unit purchase cost is $2, and unit price is $6. That means at this price you can sell it. And what we are assuming, there is no ordering cost, or the ordering cost is negligible. We know there is a static inventory problem, so that's why just one order is to be placed. And suppose the ordering cost is ordering the process or the procedure you follow for placement of our order. Suppose this procedure is very simple. It's okay, hardly any cost you are incurring, is that right? So we may assume that the ordering cost is negligible, or so no ordering cost. Now with these values, so payoff matrix you must create first, as we have done before. So what are the ordering strategies? The possible ordering strategies are either 1, 2, 3, 4, 5 or 6. So all possible order strategies you consider, and with respect to, or when you consider the possible demand levels. So the possible demand levels are 1, 2, 3, 4, 5, 6. Now the payoff matrix you construct. That means here just a few examples I will tell you that how do you calculate this payoffs against a particular combination. Suppose the order quantity is 1 and your demand is 1. That means it is exactly matching. Okay, so as such there is no opportunity cost. Similarly, suppose the order quantity is 2 and your demand level is 2. So it is exact match, and that's why there is no opportunity cost. Similarly, for all these combinations, 3 versus 3, 4 versus 4, 5 versus 5 and 6 versus 6. Is it okay? So these are all diagonal elements. So if you look at these diagonal elements, so when the demand matches with the order quantity exactly, there is no opportunity cost. For all other cases, when the demand doesn't match with the order quantity, there will be some loss, and this is referred to as the opportunity cost. Is it okay? So first you construct the payoff matrix. Now here for the order quantity 1, okay, and the demand is 1, obviously you are selling, okay, because there is a demand for 1 unit. How much you will be getting? 6,1. And for ordering, how much cost you have incurred for purchasing? That is 2. So 6 minus 2 equals to 4. And how many units you have supplied? That is just 1. And for each unit you supply, there is a delivery cost, that is 0.5. So it is 6 minus 2 minus 0.5, that is 3.5. Is it okay? Now for the second case, when the demand level is 2, obviously now how much the outcome it will be just 3.5, because the other unit you cannot sell. Is it okay? So the 3.5, 3.5, 3.5, 3.5. It's clear. So it is unfulfilled demand, right? So obviously the delivery cost just for 1 unit, and the price unit price that you get, that is for just 1 unit, that is 6 minus say the 2, 4, okay, the 2, because we have just purchased 1 unit, so it remains at 3.5. Now the next one is the order quantity is 2. So how much you have spent? That is 2 into 2, 4, and the 6 units you can sell just 1. So 6 minus say the 4, the 2, and the 2 units. So 1 unit, what you can say, that you can sell extra with 0.5, but again the unit delivery cost for 1 unit, because the demand is 1 unit, you need to spend 0.5. So the 0.5 minus 0.5, that means it is 0. So it becomes 2. So if there are 2 units of demand and the 2 units of the order quantity, so how much you are spending? So the 2 into say 6, that is the sales price is, so 2 into 6, 12, minus 2 into 4, so 12 minus 4, that is 8. Now what you are trying to do, that means the 2 units, that means unit delivery cost, 2 into 0.5, that is 1. So 8 minus 1, that is 7, and for all other demand levels it remains at 7. Is it okay? So this procedure you have followed, and you have ultimately for all other ordering strategies for all other demand levels. So you get the this payoff matrix. I hope that the logic is made very clear, and you just you just verify each and every the payoff, say the value given in this particular table. Okay. So now, so how do you calculate the opportunity cost matrix? That means original payoff matrix, as I have already pointed out, that when the demand matches exactly with the order quantity, that means there is no opportunity cost. Is it okay? So all these diagonal elements you will find in the opportunity cost matrix table. All these diagonal elements are 0. That means there is no opportunity cost. Now supposing your demand is 1, your order quantity is 2. Is it okay? So you're getting an opportunity cost of 1.5. That means what you try to do, that means this is the maximum. That means you just select one particular column against a particular demand level. Now this is the payoff. Now first you check that what is the maximum value you get. So in this case it is 3.5. Whereas if you opt for, say, order quantity 2, how much you will be getting the payoff, that is 2. Okay. So how much you will be losing, as you are not following the best possible ordering strategies. Is it okay? So that means from the maximum value, that means you subtract that whatever the value you have got, that means it is 2. So that means 3.5 minus 2, that is 1.5. It's clear? Now this value, the payoff, you will find it is 0.5, but the maximum you could have obtained, that is 3.5. So that means you are losing a value of 3. Okay. So similarly for all other the combinations, okay, so you calculate the opportunity cost. That means here if your demand is 1 and if you place an order quantity of 6, that means you will be losing 7.5. Okay, 7.5 say the dollars. So that is the opportunity cost. So the same logic you follow here for the second column. What you find, that this is the 2 into 2, that means demand level is 2 and the order quantity is 2. You get the maximum possible return, that is 7. Is it okay? Whereas if the order quantity is 1, you get a value of 3.5. So how much you will be losing, that is 7 minus 3.5, that is 3.5. So this logic you follow, right? That means from when the original payoff matrix is in terms of say the profit, so go to a particular column, you select the maximum value and you subtract the actual value from the maximum value, and you get against a particular column all the opportunity cost values. Okay, so this logic you follow. I suggest that for all other columns you verify this logic, and you must know that how you are getting each and every value. Is it okay? So this way you convert the original payoff matrix into the opportunity cost matrix. Okay. So what we try to do essentially, that either you use the opportunity cost matrix table, or you can also use the payoff matrix table, and against each say the order quantity or the ordering strategies, you calculate. Okay, you go row wise, you calculate the expected payoff. Is it okay? So expected payoff, and you select that particular strategy where the expected payoff is maximum if the original payoff matrix is in terms of the profit. Whereas if its original payoff matrix is in terms of cost, that means again you calculate against each ordering strategy the expected payoff in terms of the cost, and you select that strategy for which the expected cost is minimum. Whereas if you convert the original payoff matrix in the opportunity cost matrix, like we have done here in this particular case, what you need to do, that means you refer to the opportunity cost matrix against each ordering quantity, you calculate expected opportunity cost. Like for this one, the first row, you calculate the expected opportunity cost. Against each demand level, there is a probability associated with it. Is it okay? So you calculate the expected opportunity cost and you select that particular say the strategy where the expected opportunity cost is minimum. Is it okay? So this way you have understood that already that given a particular problem in this category, static inventory problem under risk, how to construct the payoff matrix, how to convert the payoff matrix into the opportunity cost matrix, and how to get a solution. Now here your the criterion which you are using for selecting the best possible order strategy, that is the expected payoff. So there could be many other the cases where the criterion may not be the expected profit or expected cost or expected opportunity cost. So later on we will be referring to those problems where for selection of the best possible ordering strategy we need to use some other criteria. So we explain in the next cases, the next lecture sessions we will be discussing the continuous the distribution, demand distribution case. Okay, so thank you.